Development Pharmaceuticals in association with Higher Secondary Principals Forum.
Hello students, today we would be discussing about chemical kinetics. In standard 11, you have been studying about different aspects of chemical reactions. In the chapter thermodynamics, we have studied about spontaneity of reactions. The values of delta G, whenever is negative, we say that the reaction is spontaneous, it's going to be taking place on its own. But whenever reactions are non-spontaneous, we say that delta G values are positive. So whether the reaction is going to be taking place on its own or no, we could find that out by finding out delta G values. Another aspect is to find out the yield of reactions, how much of product you are going to get at the end of different chemical reactions. So this we found out by studying equilibrium constant values. Equilibrium constant values help to find out whether a reaction is going to proceed to 100% or if it's going to proceed to 50%, etc. The yield of the products you can find out by knowing the values of Kc. Now today in this chapter we are going to be studying about how fast chemical reactions are going to take place, or basically we are going to determine rates of different chemical reactions. In physics, you must have studied about speed, and we say that speed is equal to distance upon time. Here, in chemistry, we will be interested in finding out speeds of reactions, which we are going to term as rate. So rate is basically change in concentration of reactants or products with respect to change in time. Now if you see here, rate of a reaction is the change in concentration of a reactant or product in per unit time. If you consider a reaction here, a reactant giving product, the rate of disappearance of the reactant is equal to decrease in the concentration of reactant upon time taken. Alright, so here we have to understand that whenever we study reaction rates, either we look at the concentrations of the reactants changing or the concentration of products changing, and we know that whenever chemical reactions take place, the concentration of reactants go on decreasing and the concentration of products go on increasing. If you look at this graph here, it is a graph of concentration versus time, and we see that the concentration of the reactant is going to be maximum at time 0 and it goes on decreasing with increase in time, while the product concentration is going to be 0 at the beginning and it goes on increasing when the time increases and reaches a maximum. So this portion where the concentration doesn't change of the product and the reactant, we say that the reaction has reached its equilibrium, which we have done in standard 11. Now what we'll be interested in this chapter is how fast the concentration of the reactant decreases, reaches equilibrium, or how fast the concentration of the product increases and reaches equilibrium. So we say that rate of a reaction can be defined with respect to rate of disappearance of the reactant, and also it can be defined in terms of rate of appearance of product. Now if you look at this term here for rate of reaction, when we discuss about rate of disappearance of the reactant, it is given as decrease in the concentration of the reactant upon time taken, which is also equal to negative delta R by delta T. Now the meaning of delta is change in concentration from one specific time to another time unit, while in this case for rate of appearance of the product, we find that it is going to be, rate is going to be equal to delta P upon delta T. So delta P is going to be change in the concentration of product upon delta T, which is going to be change in time. Now about the negative sign here, I'm going to explain to you a little later. We will look at types of reaction rates. Now in speeds also we have something known as average speed and instantaneous speed. In average speed, we find out the speed of a vehicle for a given time interval, while in instantaneous speed, we want to know exactly what is the speed of a vehicle at a given moment of time. In the same way, in chemical reactions, we have something known as average rate and instantaneous rate. In average rate, we are going to find out the rate of a reaction, how fast a reaction is taking place for a given time interval. Suppose I want to know from 0 to 5 seconds what is the rate of the reaction, then we can do that by using average rate. While in case of instantaneous rate, we are going to be interested in how fast the reaction is taking place at a particular moment of time. So in 5 seconds, if I want to know what is the rate of the reaction, I can do that by calculating something known as instantaneous rate. Now average rate is given as negative delta R by delta T, and instantaneous rate is given as negative delta dr by dt. Now here delta refers to a considerable change in concentration and some time interval, so suppose 0 to 5 seconds, while d here is going to be a very small change in concentration upon a very small change in time. So we need to understand the definition of rate of a reaction. It is not just concentration upon time, it is change in concentration upon change in time. So there has to be some change in concentration which we bring nearly equal to 0, not equal to 0 but nearly equal to 0, and that's why we represent delta as d for instantaneous rate, because we want to know at a particular moment of time what is the rate of the reaction. So this is these are the two types of reactions here, reaction rates. Now the average rate, if you have to calculate, there is a plot here of concentration versus time. The concentration of the reactant is shown here because as you can see it is maximum at time 0 and it goes on decreasing as the time increases. Delta R, that is average rate, if you have to calculate, it's negative delta R upon delta T. Here I'll explain to you why we use the negative sign also. Delta R refers to R2 minus R1. R2 is known as the final concentration of the reactant and R1 is the initial concentration of the reactant. So if you look at the plot here of reactant decreasing at point, suppose T1, I mark this as T1 here, at some point T, the concentration of the reactant is considered as R1, while at some point T2, the concentration of the reactant is considered as R2. So R1 here is the initial concentration that we get initially when the reaction is taking place, and R2 is going to be considered as the final concentration when we want to calculate the average rate for this time interval, that is between T1 and T2. R2 becomes final concentration of the reactant and R1 is the initial concentration of the reactant. So when you subtract the final concentration with the initial concentration, that is nothing but delta R, while delta T is going to be T2 minus T1, the time required to reach the final concentration, and T1 is the time required to reach the initial concentration. That's how we calculate average rate. Now for instantaneous rate, as I said, instantaneous rate is the rate of the reaction at a given time, particular moment of time, not interval but particular moment of time. So suppose you want to find out what is the rate of the reaction at this point here on the graph. So you're not looking at a time interval, you're just looking at a point. So at this point here, if you want to calculate, then you just have to draw a tangent to the curve and then calculate the slope of that tangent. That's how you calculate instantaneous rate. So in instantaneous rate, even if the values are given to you, you won't be able to calculate instantaneous rate because you need to know the plot. You need to plot a graph and you have to calculate it using a slope to the curve, draw a tangent to the curve and then calculate it using the slope. So that's going to be instantaneous rate. Here in this example, there is instantaneous rate calculated already and given to you. There are two particular points selected here on the line and the slope is calculated. So let me repeat that instantaneous rate is calculated as negative dr by dt and it can also be given as negative slope. Now here in the previous slide, if you see average rate, let me explain to you why we use the negative sign whenever we calculate average rate with respect to change in concentration of reactant. We need to understand that the reactant concentration goes on decreasing as the time increases. So whenever we take the final concentration as R2 and the initial concentration as R1, R2 will always be a lower value compared to R1. And when you subtract this lower value with the higher value, you are going to get a negative answer. That is, so suppose if I take R2 concentration as 10 moles per liter. Normally the units of concentration is moles per liter. And if I take the concentration of R1, which is going to be higher, as 20 moles per liter, then if I have to find delta R, which is given as R2 minus R1, it would be equal to 10 minus 20, and this would give you a negative answer, which is going to be negative 10. And we need to understand that speeds or rates of chemical reactions cannot be negative, and that's the reason whenever we discuss about average rate or rate of a reaction, in terms of concentration of the reactant, we introduce a negative sign. This negative sign is only used to make the overall rate positive, and there is no other need of the negative sign. The need of the negative sign here is only to make the overall rate of the reaction positive. So I have not calculated the rate here, I have just shown you how the concentration of the reactant affects the rate of the reaction and makes it negative, and therefore we use the negative sign. The time interval here, again T2 is going to be T2 minus T1. So T2 will always be a higher time value and T1 is going to be a lower time value. So if it's 10 and 5, it's going to be 10 minus 5, that will give you a positive answer. So what gives you the negative answer is the change in the reactant concentration, because concentration of the reactant goes on decreasing with time. While in case of product, for product concentration, we don't have to multiply it by a negative sign, because the product concentration goes on increasing as the time increases. So whenever we take the final product concentration, suppose I take this point as the final product concentration and this point as the initial product concentration, then the difference between the two will always give you a positive answer, because it goes on increasing. While if you have to consider for the reactant, it will always give you a negative answer when you find out delta R. Delta P will be positive always and delta R will be negative always, and therefore we have to just be careful of introducing the negative sign here. Alright, so we've seen how to calculate average rate and instantaneous rate. Average rate can be calculated with the values that are given to you, while instantaneous rate you need to understand that you have to plot a graph and then calculate instantaneous rate. Now what are the units for rate of a reaction? We've seen that rate of a reaction is basically concentration, change in concentration upon change in time. So the concentration units, if you're going to take moles per liter, then the unit of time can be taken in seconds, it can be taken in minutes, it can also be taken in hours. And therefore the unit of the rate of reaction is going to be change in concentration, which could be moles per liter, upon change in time, could be either seconds, minutes or hours. The total unit is going to be mole per liter per second. Now we need to also learn here how to write down rates of reactions in terms of reactant and product concentration. Here if you look at a reaction, mercury and chloride reacting to give you mercury chloride, the rate of the reaction can be written in terms of reactant as well as in terms of product concentration. Now whenever we write the rate in terms of reactant concentration, it's written as for mercury negative delta Hg upon delta T. Now here you need to understand I've written average rate and not instantaneous rates. You could also write the instantaneous rate, you have to just replace delta by D here, because that represents a very small change in concentration. So it's given as negative delta Hg by delta T. Rate of the reaction can also be written in terms of chlorine, and it's given as negative delta Cl2 by delta T. And in terms of product HgCl2, it's given as delta HgCl2 by delta T. Now here Hg in bracket refers to change in concentration of mercury. Cl2 in bracket again is going to be change in concentration of Cl2, chlorine. That's how we are going to write. Now here you have to pay attention that if you look at the number of moles reacting, there is 1 mole of mercury reacting with 1 mole of chlorine to give you 1 mole of mercury chloride. So whenever you calculate the rate of the reaction, it's not going to be affected because the number of moles is just 1. Every time 1 mole of mercury and chlorine disappear, there will be 1 mole of mercury chloride appearing at the same time. Okay, so that's how you write down the rate of the reaction with respect to different reactants and products. Here you have to pay attention when the number of molecules of the reactant and product is not the same. As you see, hydrogen iodide is the reactant here, which are 2 in number, 2 molecules or 2 moles have been used, and you have 1 mole of hydrogen and 1 mole of iodine being produced every time 2 moles of hydrogen iodide is being used up. So in that case, whenever you write down the rate of the reaction in terms of the reactant, you have to remember to put the negative sign because reactant concentration keeps on decreasing with time, and also you have to divide the stoichiometric coefficient by the rate of the reaction. So we know that the rate of the reaction is calculated as concentration, change in concentration upon change in time, but we have to divide it by 2 here because every time 2 hydrogen iodide molecules are used up, there is 1 of hydrogen and iodine being produced. So that's the reason the rate is going to be half here of the amount of time that's going to be taken for hydrogen and iodine to be produced simultaneously. So what you have to remember here, whenever the chemical reaction, whenever a balanced chemical reaction have different number of moles for the reactants and the products, then while writing the rate of the reaction in terms of reactants and products, we have to see that the stoichiometric coefficient is divided by the rate of the reactant or the product. Alright, so if suppose I had 2 molecules of hydrogen here, I would have to divide this entire rate by 2. If I had 3, I would have to divide it by 3. So this is what you need to remember, and you should be able to write down the rate of reaction in terms of reactant and product. Now the next part of this topic is what are the factors that can influence rate of reactions. The meaning of this would be, if suppose I am carrying out a reaction and I want to increase the rate of the reaction, I want the reaction to be faster, maybe it's taking 2 or 3 days for the reaction to proceed, and I want to carry it out within a day or within a few minutes or hours, then what are the different factors that could affect the rate of the reaction? The 3 factors that we are going to be studying in this unit is concentration, temperature and catalyst. We will be looking into the details of concentration first. Now what happens when the concentration of a reactant is great or is more and the concentration of the reactant is less? Whenever we start with a reaction with a huge concentration of the reactant, we find that the rate of the reaction is fast when the concentration is large. When the reactant concentration goes on decreasing, we find that the rate of the reaction becomes slower and slower. Alright, so this is practically determined. Different experiments are carried out for the same reaction, and different amount of the reactant concentration is taken. So whenever higher concentrations were taken, it was found that the rate of the reaction was faster. So that's why here we can say that the rate of the reaction is directly proportional to the concentration of the reactant. That means greater the concentration of the reactant, faster is going to be the rate of the reaction. Now the representation of the rate of a reaction in terms of the reactant is known as rate law. I have taken an example here of reactant A and B reacting to give you C and D. The rate expression here is given as rate is equal to K into concentration of A raised to X and B raised to Y. Now before this, you need to understand that suppose I have a reaction, reactant giving product, then since we know that rate of the reaction depends upon concentration of the reactant, we find that rate is going to be directly proportional to the concentration of the reactant. And when rate is directly proportional to the concentration of the reactant, we remove the proportionality sign and we put a constant. This constant here is known as the rate constant. Okay, so I have shown you for a reactant giving you product, but here in this example here you can see that the reactants here are A and B, and the rate is given as K into A raised to X and B raised to Y. Now here I could raise this to X. The value of X we are going to be discussing a little later, what exactly is the value of X, but you need to understand that the value of X or Y in this case could be equal to the stoichiometric coefficient, or it could not be equal to the stoichiometric coefficient. What you need to understand is these values are determined experimentally and not determined theoretically. Alright. So, here you just have to understand that the rate expression of any reaction is given as rate is equal to the rate constant into the concentration of the reactant. If there are more reactants, then you multiply the concentration of the other reactant as well and raise it to some power, which we are going to find out in the next topic. So, after we have seen that this is the rate expression, the differential form of the rate expression, because we know that rates can also be written in terms of reactant and product concentration. So, if it has to be written in the terms of reactant concentration, then it is written as negative dR by dt. This is the instantaneous rate that I have written down here. In case of average rate, you would write it as negative delta R by delta T. So, I have just replaced the word rate here by the differential form, which is negative dr by dt, and I have kept this constant, that is k into a raised to x and b raised to y. So, this equation when you write down is known as the differential form of the rate expression, and this is just the rate law expression. Alright. Now, next we are going to be focusing on these values, what I explained to you earlier, x, and how to find out the value of y. We do that by knowing something known as the order of the reaction. Order of the reaction is nothing but the sum of the powers of the concentration of the reactant in the rate law expression. The meaning of this is, suppose in the earlier slide here, the concentration of A is raised to x and the concentration of B is raised to y. The sum of x and y here is known as order of the reaction. So, this is the rate law expression. These are the concentrations of the reactants A and B. Sum of x and y is going to be equal to order of the reaction, which is given as n. Now, in this particular example, the order would be equal to x because there is just one reactant here. Therefore, whatever concentration of the reactant is, whatever is the power that it is raised to, that is going to be equal to the order of the reaction. So, that is basically the definition here of order of the reaction. Now, there is an example given here. Suppose you have a rate law expression as rate is equal to k into concentration of A raised to 1 and B raised to 2. Then the order would be the sum of the powers, which is 1 plus 2, 3. So, this reaction would be said to follow third order kinetics. Now, here as I said in the beginning, the instantaneous rate cannot be determined just by knowing the values. You have to plot a graph. Here, order of the reaction also cannot be determined theoretically. You cannot just look at a reaction and tell what the order of a reaction is. Practically, you have to carry out some experiments and you have to find out what is going to be the order of the reaction. So, basically order of the reaction tells us how much dependent is the rate of the reaction on the concentration of the reactants. Alright. Now, in order of the reaction, here there is a table which will help us to calculate order of reactions. So, there are 4 experiments that have been carried out and the concentrations of nitric oxide and oxygens have been mentioned. So, it is a reaction of nitric oxide and oxygen to give you the products. So, we are going to be interested in how the concentration of nitric oxide and oxygen changes with time. So, in the first experiment, what is done is the initial concentration of nitric oxide is kept as 0.3 moles per liter and the concentration of oxygen is taken again as 0.3 moles per liter and the rate is calculated as 0.096. In the second experiment, the concentration of nitric oxide is changed from 0.3 to 0.6. So, this is a separate experiment. The same reaction, but there are 4 different experiments carried out. In the second one, we have 0.6 moles per liter of nitric oxide. It has almost been doubled the concentration, while the concentration of oxygen is changed from 0. It's fixed. It's 0.3 only, and the rate is changing from 0.09 to 0.384. In the third experiment, the concentration of nitric oxide is 0.3, oxygen is 0.6, and the initial rate is 0.19. And there is a fourth experiment again with different concentrations of nitric oxide and oxygen. Now, if you want to calculate the order of the reaction, first we should be able to write down the rate law expression. To write down the rate law expression, we write the rate law expression as rate is equal to K into concentration of nitric oxide raised to X into concentration of oxygen raised to Y. So, what we are doing here is trying to find out what is the value of X and what is the value of Y, which is nothing but the order of the reaction. Now, to do that, we are going to use this data that is given to us. Now, in this data, let us consider the experiments where the concentration of nitric oxide is not changed and the concentration of oxygen changes. So, we would consider the first experiment and the third experiment. We will omit the second and the fourth one. So, in the first experiment, we find that the concentration of nitric oxide is 0.3, it is constant, it is not changing in the third experiment, while the concentration of oxygen changes from 0.3 to 0.6. The rate of the reaction changes from 0.09 to 0.19. Now, we need to understand that the concentration of oxygen changes from 0.3 to 0.6, that means it is doubling. Initial rate 0.09 could be rounded up to 0.1. And 0.192 could be rounded up to 0.2. Alright. So, we find that the concentration of nitric oxide is not changing. Here K is a constant, it is known as the rate constant, which is not going to change for the reaction. N, concentration of nitric oxide, is kept constant. So, this entire term is going to be a constant. What is changing is only the concentration of oxygen from 0.3 to 0.6. It is changing 2 times. So, we are going to write 2 here. And we find that the rate of the reaction, since it is changing from 0.1 to 0.2, again it is changing 2 times. Now, here we need to understand that when we keep these terms constant, what has to be raised to 2 so as to get the answer as 2 for rate of the reaction. And we find that the value of Y should be equal to 1, because 2 raised to 1 is going to be equal to 2. So, using this table, we have calculated how to find out the value of Y. Now, we need to find out the value of X. To determine the value of X, we have to keep the concentration of oxygen constant. So, in that case, let us take the first and the second observation. Now, in the first and the second observation, we find that the concentration of oxygen is not changing, it is 0.3, but the concentration of nitric oxide changes from 0.3 to 0.6. That means it is doubling. While if you look at the rate changes from 0.09 to 0.384. Now, 0.384 we can round it up to 0.4. So, we find that the rate is 0.1 in the first experiment, changes to 0.4 in the second experiment. So, now if you have to calculate rate, we keep the rate constant and concentration of oxygen to be a constant. So, we are not going to bother about the change in the concentration of oxygen. While the change in the concentration of nitric oxide, we find that it is increasing 2 times in the first and the second observation, from 0.3 to 0.6. So, it is increasing 2 times, and the rate of the reaction is changing from 0.1 to 0.4. That means it is increasing 4 times. Now, we need to find 2 has to be raised to what unit so as to give you 4 as the answer, and that is going to be 2. So, the value of X here is going to be equal to 2. Now, in this data that is provided to us, we try to calculate the order of the reaction. Not as yet. We found out that the rate of the reaction with respect to oxygen, the order is going to be 1, and with respect to nitric oxide, the order is going to be 2. But the overall rate of the reaction, remember, it is the sum of the powers to which the concentration terms are raised, which is N would be equal to X plus Y, which is going to be 2, plus 1. So, the overall order is going to be 3. It's supposed to be a third order reaction. So, this is how order of reactions can be calculated. You need to understand that they are practically determined values. Now, suppose there is no other information given to you, or just given a balanced chemical equation and you are supposed to write down the rate law expression, then in that case you could use stoichiometric coefficient as the powers that you are going to raise the concentration terms to, alright. Otherwise, you have to look for the rate law expression, and if the values of x and y are given to you, then the order is going to be the sum of the powers. Now, another important part here that we have to discuss is what is molecularity of a reaction and how it is going to be different from order of a reaction, because we need to compare molecularity and order. Molecularity, it is the number of reacting species, that is atoms, ions or molecules taking part in an elementary reaction. Now, what is the meaning of elementary reaction? Elementary reactions are those which are simple reactions taking place in just one step, because you can have something known as complex reactions. In complex reactions, the reactions take place in several number of steps. So, you could use this molecularity only for determining, to find out molecularity in elementary reactions. Now, you need to understand that in an elementary reaction, whatever are the number of reacting molecules that are going to be taking part in the reaction, the molecularity would be equal to the number of those reacting molecules, which will collide simultaneously and give rise to products. So, examples here would be, what is a unimolecular reaction? Whenever you have just one reacting molecule, it is said to be unimolecular. For bimolecular, you have two reacting molecules and it is going to be bimolecular. Example here is hydrogen iodide, giving you hydrogen and iodine. In the balanced chemical equation, we have 2 moles of hydrogen iodide reacting to give you 1 mole of hydrogen and 1 mole of iodine. And trimolecular would be 2 moles of nitric oxide reacting with 1 mole of oxygen to give you 2 moles of nitrogen dioxide. So, the molecularity here is going to be 3 because you have 2 of nitric oxide and 1 of oxygen reacting. Now, we need to understand the difference between order of a reaction and molecularity. The first point would be basically how would you define order of a reaction. It is the sum of the powers to which the concentration terms are raised to in a rate law expression. And molecularity would be just, if you look at a balanced chemical equation, what would be the number of reacting molecules? That is going to be molecularity. You need to remember that it has to be an elementary reaction or a simple reaction. The other difference is that order could be fractional. It does not have to be just numbers 1 to infinity. It could be a fraction. It could be even a 0, because we have reactions which are 0 order. 0 order means that the rate of the reaction does not depend on the concentration of the reactant. How much ever you increase the rate of the concentration of the reactant, the rate of the reaction is not going to change. So, that would be an example of a 0 order reaction. While molecularity can never be 0, because you cannot have 0 molecules colliding to give you products. You have to have some amount of reacting molecules to collide and give you products. So, molecularity is always non-zero and it is a non-integer. And the third point would be order is mostly determined experimentally. By looking at a chemical equation, you cannot find out what is the order of a reaction. You need to have some experimental data and you have to see how the reactants react and how the rate of the reaction changes with respect to the reactants. While molecularity, you can just look at a chemical equation. If it is an elementary or a simple equation, then we can find out what the molecularity is going to be by looking at how many reactant molecules are present. And the final point of difference is going to be, it is applicable for elementary as well as complex reaction, that is order. You can find out order of a reaction for a simple reaction and also for a complex reaction which has many number of steps. In a complex reaction which has many number of steps, the slowest step is known as the rate determining step. So, that will help us in finding out the order of the reaction. While in molecularity, the reactions have to be elementary reactions. So, now in this class, what we have done is we have studied what is rate of a reaction. We have seen what is the difference between order and molecularity of a reaction. Now, I will be explaining to you about integrated rate equations. Now, what we are going to do is, we would be studying about integrated rate equations. Now, what is the use of integrated rate equations? We know that instantaneous rates cannot be calculated by just giving you some values. You have to plot a graph and it is going to be a very tedious process. So, to convert the differential form of the rate equation to an integrated form, it's going to be better because it's going to help us in calculating rate constants, times as instantaneous rates. So, here what we have to understand is how to derive integrated rate equations for 0 and first order reactions, and also we need to find out how they are going to help us in calculating different values of rate constant for different numericals which you can be asked. So, you have to pay attention to how the equation is derived because it can be asked for you for your exams. You need to know the derivation. So, here right now what we are going to do is derive integrated rate equations. First we are going to derive an integrated rate equation for 0 order reaction. Now before we start with the derivation, you have to know a few formula in mathematics. Even if you are not a math student, if you know the two formula that we are going to use in the derivation, one would be integral of x dx is equal to an integral of dx and so if you keep this formula in mind, it's going to help you in the derivation. Integral of x dx is given as x raised to n plus 1 upon n plus 1 plus c. Integral of dx would be x plus c, and integral of 1 upon dx is going to be ln of x plus c. Alright, so I will keep this formula which we are going to use while deriving the final equation. So for 0 order reaction, we know that for a reactant giving you some amount of products, for any reactant giving you product, the rate of the reaction in terms of reactant concentration is given as minus dr by dt. Alright, in terms of reactant concentration, we write the rate in this way. In terms of the rate law expression, we write rate is equal to K into concentration of the reactant. Now since we have considered that the order of the reaction is 0, we would substitute the value here as 0. So rate here will be equal to K, and instead of writing the word rate, we could write the differential form by using this, and therefore instead of rate I would write minus dr by dt is equal to K. Now on rearranging these terms, dr is equal to K dt. Let us just take this as equation 1. Now what we are going to do is, we will try and integrate this equation. Alright, this is change in concentration of the reactant, change in time. So on integration, integral of dr will be equal to K is a constant, so it does not come under the sign of integration, would be integral dt. Now integral of dx is supposed to be x plus c, where c is known as the constant of integration. So integral of dr is given as r plus the constant of integration, which I am going to write later, equal to K. Integral of dt would be equal to t plus, I will write I here. We are going to have a constant here for t as well as for r, which I am going to write together as I. So I here is the constant of integration. Alright, now we take a condition. Suppose T is equal to 0, that is at the start of the reaction where we just take the reactant in the reaction vessel and we are carrying out the reaction. So at time 0 we consider the concentration of the reactant R to be equal to R naught. Now the meaning of this is at a particular time T the concentration of the reactant is R, but if the time is taken as 0, the concentration of the reactant is termed as R naught, which is known as the initial concentration of the reactant. Alright. So if we take both these conditions, then we are supposed to substitute these values in the above equation, which I have marked as 2, and we find that instead of R, we are going to write R naught is equal to K into T is taken as 0 plus I, and if you further solve it, you get this as R naught is equal to I. Now using this value of I in equation 2, instead of I we are going to write R naught because we found that I is equal to R naught. We could rewrite equation 2 as R is equal to KT plus R naught. Now this is an important form of the equation, alright. Here we have to take the negative sign, because it's reactant concentration, and if you look at this equation, it is of the type Y is equal to mx plus c. Okay, we could further rearrange the terms and find out what is the value of K, and if you rearrange the terms you find out that K would be equal to R naught minus R upon T. Alright, so this is the final equation. If you want to calculate rate constant for a zero order reaction, then we need to know what is the initial concentration of the reactant, what is the final concentration at time T. Now why have I marked this here? Because we should be able to plot a graph showing the reactant concentration and time, how it varies with time. So if you have to plot a graph, the nature of the graph is going to be, here you are going to have the reactant concentration, time, and since we have an intercept here on the y axis which is R naught and the reactant concentration is considered, we find that as time increases the concentration of the reactant goes on decreasing. The nature of the graph is going to be this. Initial concentration at time 0, we have considered it to be R naught, which is here, which is the intercept, and m, which is the slope, is given as minus k. So the slope of this is going to be negative since the concentration of the reactant goes on decreasing with time. So this particular equation helps us in plotting a graph of reactant concentration versus time. So in this derivation you should understand that you have to learn how to derive the equation right from some reactants giving you products to what is the value of the rate constant R naught minus R by T for a zero order reaction. Alright, so this derivation can be asked, and you can be asked different questions on the graph. So you should know what it is a plot of on the x and the y axis, what is the slope equal to and what the intercept is equal to. Now along with this, what else can be asked is how to derive a first order reaction. So the derivation is done in the same way, almost the same way, with a few exceptions, because now we are not going to take the order as 0, but we are going to take the order as 1. Now for a first order reaction, we have to see what is going to be the value of the rate constant. We are going to start in the same way as we've started with zero order reaction, that is reactants giving you products. We know that we could write down rate is equal to K into concentration of the reactant. Now it's raised to 1, or you don't write anything, then it's assumed that it's raised to 1. Rate in the differential form can be written as minus dr by dt is equal to K into the concentration of the reactant. Now I'm just going to rearrange the terms. Dr would be equal to minus K dt, and I'm going to take R on the other side, concentration of the reactant. After rearranging the terms, now we are going to use integration, and we are going to integrate this differential form of the equation. So on integration, we find that integral of 1 by r dr, I have just written it as 1 upon r dr, it is the same as dr by r, which is equal to minus K integral dt. K is a constant, again we do not integrate a constant here. So when we integrate this, we have a formula here which I had mentioned earlier. Integral of 1 upon x dx is equal to ln of x plus c. So integral of 1 upon r dr will be equal to ln of r plus the constant of integration, which I am going to write later, minus k t plus I, which is the constant of integration. Now again we are going to use the same conditions. Let T be equal to 0, then the concentration of the reactant at time t would be equal to R naught, which is the initial concentration of the reactant. So if you have to substitute these values in equation 1, we are going to get ln of R naught is equal to minus K into 0 plus I. And finally we get I is equal to ln of R naught. This value of I we are going to substitute in equation 1 and rewrite the equation as now we have to rearrange the terms. Keep K on one side, get all the other terms on the other side, and you are going to get this final equation. Now to use this equation to solve numericals, it is going to be a little difficult for us because normally we are given common logarithms, and to convert natural logarithm to common logarithm we multiply by a factor 2.303. So to do that, the final equation we can write as 2.303 K is equal to 2.303 upon T log of R naught upon R. Now this is the second derivation that we have done. We have derived an integrated rate equation for the rate constant of a first order reaction, and we find that it is equal to K. K is equal to 0.303 upon T log of R naught upon R, where R naught is the initial concentration of the reactant and R is the concentration of the reactant at some time T. Now using this equation, we can plot a graph in the same way like how we did for zero order reaction. Here y is going to be mx and this is going to be c. So if you have to plot a graph, we are going to plot it as, on the y axis we are going to take ln of r. On the x axis we are going to take time t, and again the nature of the graph is going to be concentration of the reactant goes on decreasing with time. The intercept here is ln of R naught, and the slope is going to be equal to minus k. Alright, so this is the way the plot is going to be for this particular equation, and you need to know what comes on the x and the y axis, what is going to be the slope and what is going to be the intercept. You should be able to even differentiate with respect to the graph that I have drawn right now and the graph that I had drawn earlier for zero order reaction. Now another graph that we could plot using this equation is when I just rearrange the terms again of the final equation, that is k is equal to 2.3 naught 3 upon t log of r naught upon r. Suppose I keep log of r naught upon r on one side and I get all the other terms on the other side. Now if you look at this equation, it is of the type y is equal to mx. So here there is no intercept, it is going to be a straight line passing through the origin. On the y axis you are going to have log of r naught upon r. On the x axis you are going to have time t, and you find that the slope is going to be equal to k upon 2.303. Alright, so this is another graph that you have to learn for first order reaction, which you can plot using this equation. So now what we have seen is how to derive rate constant for first order and zero order reactions. Now examples of zero order reactions would be any reactions that involve a solid catalyst, because in such reactions how much ever you increase the concentration of the reactant, the rate of the reaction is not going to get affected, because whatever is the number of molecules that can adhere on the surface of the catalyst, that would determine the rate of the reaction. So increasing the concentration of the reactant would not help. So basically those are going to be examples of zero order reactions. First order reactions, you can have reactions which are radioactive decay of unstable isotopes. So they mainly follow first order kinetics. So these are a few examples of zero and first order reactions. Now besides these two derivations that we have done, there are another two derivations which are a bit more simpler than what we have done now. So you have to practice both these derivations. The other two derivations are based on another concept which is known as half-life of reaction. Now half-life of reaction is given as T half. What is the meaning of half-life of a reaction? Suppose I start with a reaction having initial concentration of 10 moles. So let me consider this as R naught, that is initial concentration of the reactant at time 0. Suppose it is 10 moles. The time that it takes for this 10 moles to reduce to 5 moles, which is half of 10, the time that is taken, that time is referred to as half-life or T half of a reaction. So half-life of a reaction is nothing but the time taken for the initial concentration of the reactant to reach half the amount. Now we are going to look at equations wherein we can find out or we can calculate half-life of different reactions. We are going to again look at only zero order and first order reactions. Now how to derive what is the value of T half for a zero order reaction? We could directly take the rate constant expression that we have derived for zero order as K is equal to R naught minus R upon T. We have already derived this equation earlier. We are going to use this equation to find out what is the half-life. Now for half-life, we have to consider the time T equal to T half. That is the time taken for the reactant concentration to reach half the amount, initial concentration. So in that case, when T is T half, the final concentration R should be equal to half the initial concentration, because that is the definition of half-life. The final concentration, when it is half the initial concentration, that time taken is known as T half. So when T is T half, R is equal to half of R naught. Now we are going to substitute these values in the above equation, and we find that K will be equal to, instead of R, we are going to write half of R naught divided by T half. T is substituted as T half. So if I take T half on the other side, it's going to be equal to R naught minus. Now you need to understand that R naught minus half of R naught would be, suppose I take R naught as 10 moles, half of R naught is going to be 5 moles. So 10 minus 5, the answer is going to be 5. So R naught minus half of R naught will always be equal to half of R naught. So instead of writing R naught minus half of R naught, I am going to substitute it as half of R naught. Take 2 down in the denominator, and K, which we have brought from the other side of the equation. So we come to this equation, final equation of half-life of a reaction for 0 order. T half is equal to R naught upon 2K. We find that the half-life is dependent on the concentration of the reactant, initial concentration of the reactant directly, and it is also dependent upon the rate constant. We have seen what is half-life of a reaction for 0 order. Now we are going to see what is half-life of a reaction for first order reaction. For first order reaction, again we are going to take the value of rate constant K for first order, which is 2.303 upon T log of R naught upon R, which we derived earlier. We are going to use the same conditions here. If T is equal to T half, then the concentration of the reactant R would be equal to half of R naught. We are going to substitute these values in the above equation, which would be 2.303 upon T half into log of, here R naught is going to remain as it is. The value of R we are going to substitute as half of R naught. So when we substitute half of R naught, we can take 2 in the numerator. You need to know the value of log 2. Log 2 value is 0.3010. When you multiply 0.3010 with 2.303, we get the answer as so T half is equal to this is going to be the final equation for half-life of a reaction of first order. So we need to know how to derive T half for 0 order and also how to derive T half for first order reactions. The final equations are important, the derivations are also important. So in all today we have done 4 derivations, that is rate constant of 0 order, first order reaction. Derivation is important, the final equation is important, you can be asked numericals on these equations, and also half-life of a reaction.
Prudent Scholars, powered by Lupin Pharmaceuticals.